So in this lecture, we are going to look at the Wittig reaction. Now, the Wittig reaction is one of the reactions of carbonyl compound in such a way that the carbonyl compounds of either an aldehyde or a ketone will be converted to an alkene with the formation of a triphenyl phosphine oxide. So now we have our species that reacted here. This species, the first one here, is called either the aldehyde or the ketone. So I can say this is the carbonyl compound because there's no specified one here, although this is a ketone. So we say this is a carbonyl compound, in brackets, particularly a ketone. Now, how about this? This is a phosphorus yield. Phosphorus yield. Now, what is the phosphorus yield like? Phosphorus yield is a compound, phosphorus compound, that actually have both a negative and a positive charge on adjacent atoms, or any compound that has both a positive and a negative charge on adjacent compound is called a yield. In this case, it is phosphorus stabilized, so we call it a phosphorus yield. Now, in this phosphorus yield, all the valency is actually very, very complete too. Valency is complete. So that is for that. Okay. Now, the phosphorus yield react with a carbonyl compound of either an aldehyde or a ketone to form an alkene, and then this is a triphenyl because you have three phenyl group here, then phosphine oxide, triphenyl phosphine oxide. Okay, so that is the general overview of what the Wittig reaction is. Now, there are different methods for preparing of alkenes, and this Wittig reaction may just prove as one of the methods for preparing alkene that may not ordinarily be prepared by other methods, or that may yield low that may give low yield by ordinary product. For instance, there are some that when you react some reactions in such a way that you are going to form an alkene, the products that are formed are usually two. One is a major product and the other is a minor product. Are we getting it? But in the Wittig reaction, a minor product in another reaction may become a major product in the Wittig reaction. So if you are looking for that product more, it means you should actually apply the Wittig reaction to get that product in larger yield as compared to other methods. So it's just one of the methods of preparing alkene from carbonyl compound by reacting it with a phosphorus yield, which I said is a phosphorus yield is a phosphorus stabilized carbanion that has both negative and positive charge on adjacent atoms. Are we getting it now? So that is that. Now, when this react with this, we say it's going to form an alkene with a triphenyl phosphine oxide. So what we are going to look at next is how do we synthesize this phosphorus yield, or how is the phosphorus yield synthesized? Now, the phosphorus yield is prepared from triphenyl phosphine and alkyl halide in two steps. It is prepared from triphenyl phosphine and alkyl halide in two steps. So what is the structure of triphenyl phosphine? Now, from the name, phosphine means you have phosphorus, okay, then with two lone pairs of electron. Of course, everyone knows that phosphorus is a group 5 element, so it will have a 5 valence electrons in its outermost shell. Okay, so we have the phosphorus, the phenyl group. This one phenyl, this is another phenyl, and this is the last phenyl. So you have three phenyl. That is why you call it triphenyl phosphine. Now, when triphenyl phosphine reacts with an alkyl halide, let's say alkyl bromide or any of the alkyl halide. Now this is this. Now the alkyl halide you should react with, it should be a primary alkyl halide. Okay, should be a primary alkyl halide so that there would be no hindrance, or there will be no steric hindrance. So if it reacts with this, what do you think will be formed? What will be formed is Everybody knows what this lone pairs of electron is by now. The two lone pairs of the lone pairs of electron actually mean that that particular atom or that particular molecule is a nucleophile, and this lone pair of electron can actually attack this carbon here. Now, if this lone pair of electron is coming to attack here, what do we say? That there will be a bond that will be formed between carbon and phosphorus. Are you getting it now? And as that bond is being formed, it means that we'll now be having how many bonds? 1, 2, which is this one, 2, 3, 4, 5. And of course, we all know that carbon ought to have a valency of how many? Just 4. So as this group is coming in here to make the bond to be 5, the more labile living group. When we say the more labile living group, it means the halogen, which is designated with X. This is the halogen, okay? The halogen will be broken off. Are we getting it? Now, if this halogen is broken off, it means there will be no halogen here again. Are we getting it now? So it will form X negative outside here. Then this phosphorus and this mix together to give a product. Now, the product that will be formed is something like this. You're going to have the phosphorus, which is this. Then you are going to have the phenyl ring. The phosphorus is positively charged. Please take note of it because it has donated one of its electrons to carbon. So here becomes positively charged. Then here becomes phenyl. Then phenyl. And then finally phenyl. Okay. And then you are going to form this phenyl. Okay, and then you are going to form this carbon, and then you form hydrogen, and what? Hydrogen, which is, okay, this under here is not hydrogen, this is an alkyl group here. Okay, so this structure now, which is this alkyl halide, has now bonded with this triphenyl phosphine. Are we getting it now? Now, at this point of this reaction, this is not the halide that we needed. Are we getting it? This is not the halide that we needed. Now, the next step of this reaction, so we'll form the first step. Are we getting it now? So this first step, now the question is, what's the name of this product that is formed? This product is called a phosphonium ion. Okay, this product is called a phosphonium ion. Okay, now this phosphonium ion that is formed now, or the phosphonium salt, let's take it as that, the phosphonium salt. But we said that the halide, it has both positive and negative. All we've just formed is the positive. I know how the positive came about. You know, there are 2 electrons here, right? That were only for phosphorus. But if these 2 electrons are forming bond with carbon, it means that phosphorus has donated 1 electron to carbon, right? And in chemistry, whenever you donate electron, what happens to the atom that donates? It becomes positively charged. That is why we say this one here becomes what? Positively charged. But we need a negative charge on the carbon. Now, how do we achieve that negative charge? We only achieve that negative charge when something, a base, must have come to abstract a proton from this carbon here in such a way that this bond can kick in to form a negative charge here. Okay, now how do we achieve that? We achieve that using a butyl lithium. We achieve that using what? Butyl lithium. So let's take it. That is the second step. Say the potassium or the phosphonium salt is treated with a strong base, usually butyl lithium. So butyl lithium is a strong base. When we treat it with the phosphonium salt, what are we going to have? We're going to have pH. This is phenyl. Of course, we know this is phosphorus, positively charged. This is another phenyl, because it's triphenyl. And this is the last phenyl. Okay? And then you have C. And then this is what? Hydrogen. This is hydrogen. And then this is alkyl group. Now, when you treat this with butyl lithium, the structure of butyl lithium is in this manner. You have CH2 Li. Then let's make it like this: CH2 CH2 CH3. This butyl lithium is still the same thing, no matter how you want to draw it. If you want to draw it in a straight line, still fine. Are you getting it? This butyl lithium. So what happens is the butyl lithium abstract a proton. Now this double bond here is a perfect nucleophile. Are we getting it now? This, not double bond, rather this bond here is a perfect nucleophile. So this nucleophile comes here, it abstracts a proton from this carbon. Now we said in our other videos that whenever a bond abstract a proton or a nucleophile abstract a proton, it's only taking the proton out, that means H plus out, but the electrons will still remain. So it means that this bond will still remain here, because there's one electron here for hydrogen and there's one for carbon. But if you are taking a proton out, it means that the electron of hydrogen will still remain. So this bond here, that electron that is remaining, will have to kick into this place. Are we getting it now? So if it kicks in here, it forms the negative charge that we are looking for. So the product of this reaction would be, you form pH, the phenyl group, then this is positive, and then you have phenyl, and then you have phenyl, and then you have C, and then here will be what? If you have C, here will be what? Negative, right? Here will be negative, and then you have the hydrogen, because one of these hydrogen is no longer here again. So you have one hydrogen here, and then you have the alkyl group here. Now this product formed is what is called a phosphorus yield. Are you getting it now? It's what is called the phosphorus yield. Now this yield can undergo what is it called? Can undergo why am I forgetting this? This yield can undergo resonance. That means it can have more than one resonance structure. So the other resonance structure is in such a way that this double bond kick into, the negative kicks in here, then it forms a double bond between here, and then counteract the effect of this positive charge here. So in that resonance structure, say resonance are interconvertible, so you must show with this double arrow like this. You are going to have phenyl, and then you have phosphorus, and then you have phenyl, and then you have phosphorus, this phenyl, then you have a double bond here, okay, then carbon, then hydrogen and arrow. But this form here is more stable, and that's what is used for the Wittig reaction. Okay, this form is more stable, and that's what is used for the Wittig reaction. So this is the phosphorus yield that would further react with either an aldehyde or a ketone to form the product of Wittig reaction, which is an alkane with a triphenyl phosphine oxide. Okay, so now let's see how the mechanism for the Wittig reaction is. Now you said the yield attacks the carbonyl to form a betaine. The yield attack the carbonyl to form what? A betaine. Now let's take any carbonyl group and then react it with a phosphorus yield, and then see the product of the reaction. Now the phosphorus yield is this is the phosphorus yield here right now. I can decide to make it easier by saying that this whole stuff here, this PPP, PHPH, these are phenyl, right? I can decide to say this phenyl should be written as PH. How many are there? How many are there? 1, 2, 3. I put bracket 3, and then phosphorus. It can also be written like this, then positive. Then you have your C negative with your H and what? R. So instead of writing this in whole time, we can decide to write it in the short form this way, okay? Right? We can decide to write it like this. So let's go back and then react it with a carbonyl compound. Let's say a hypothetical carbonyl compound using the general formula of carbonyls, okay? So this will be equal to PH3, which is the phenyl yield. Then we'll have C negative, and then you have hydrogen, and then you have arrow group, right? Now this is arrow, and then this is arrow. Let me make it easier by saying this is double bond, right? Carbon. Now arrow, right? Now if I want to make this easier so that it will be very easy for this to react, I can. This is a carbonyl compound, which we actually, this is the yield. Let me make it easier by saying this is the yield, and this is the what? Carbonyl carbon compound. Now I can decide to reorient this in such a way that when this one is coming, there will be no hindrance. Okay, if I want to orient this again, I can decide to write it this way. True or false? I can decide to remove this arrow here, remove this. It's still the same thing. Put the arrow here and then put the arrow here. Okay, so that when this is attacking, it will have a space to attack. So this negative charge now is what makes this a nucleophile. Okay, so what happens is that the negative charge here actually attacks this position. Are you getting it now? As the negative charge is coming to attack here, it's forming a bond here. And if it forms a bond, it makes carbon to have a valency of more than 4. So what will happen is that this bond here will pack up here to form a negative charge. Okay, so at the end of the day, you are going to have this equal to, the product now will be equal to, you are going to have the normal carbon, which is this carbon that react. Are we getting it? The carbon that bonded. Now let's take the phenyl group up because of the complex that is going to form, because the phenyl group can be anywhere, but let's put it up. So this becomes PH3 P positive. Then here is the alkyl group, and then here is hydrogen. Now everything you have here is still the same thing. We just have to orient it in such a way that it will make sense. Okay, we have to orient it in such a way that it will make perfect sense. That is the reason why I decided to do it like this, because you are going to form a complex at the end of the day. Okay, so this one now forms this, it forms a bond with this carbon, right? And then this will give you O negative. Okay, because this one packs up here, and then this one is an alkyl group, and then this is another alkyl group. Now this structure formed here like this is what is called a betaine. It's what is called what? A betaine. Are we getting it now? It's what is called a betaine. So we said the halide attacks the carbonite to form a betaine. Now the next step, step 3, the betaine closes to a 4-membered ring, oxaphosphatane or oxaphosphotane. So what we are going to do is to take this one and then close it to form a 4-membered ring. It's a very simple something. So we have C, and then we have the phenyl group, which is positively charged. I mean the phosphorus group positively charged, and then the 3-phenyl group, which are very close to it. And then you have the alkyl group, and then you have hydrogen, and then you have carbon, and then you have O minus, and then you have arrow, and then you have arrow. Now when this group, what happens here is that there is a closure. Are we getting it? There's a closure. Now don't forget that oxygen is also having its lone pair of electrons here. So there's a closure. Now how does the closure occur? This bond here, this negative charge here, we form a link between this oxygen and this phosphorus, right? Because we said that negative charges are nucleophile and they can easily form bonds. So this one here form bonds here. Remember that oxygen has its own lone pairs of electron. Okay, they have its own lone pairs of electrons, so the lone pairs are also present there. So at the end of the day, this will close. Of course, everybody knows what this means. This is a betaine, okay, or a betaine. Now when this close, the product that we expected to form is something like this. You form H, C, then you are going to form P, PH3, then it's going to form this ring structure like this, and then you have your arrow, you have your arrow here, and you have your arrow here. Are you getting it now? So this product now is what is called the oxaphosphatane or phosphatane. Now this product is what is called the oxaphosphatane. Okay, phosphatane. Now the last step, the ring collapses to form the product, or the ring collapses to the product to form alkene and triphenylphosphine oxide. Now how does that happen? The ring we had was something like this, which is the last step. The ring we had was something like this. We had carbon, then we have phosphorus bonded to what? Oxygen. Then we have the phenyl right? Then we have arrow. Then we have arrow. Then here we have arrow. And then here we have arrow. Now the ring will collapse. Now how does this ring collapse? All you just need to do is, for the ring to collapse, this one packs into this up here. This bond here breaks, packs into this up. Why this one here breaks and then pack into this place here? Are you getting what I'm trying to do? It means this bond here comes here. When this bond here comes here, it means that there will be no bond here, right? So we can now say that this bond is out. And when it comes here, what will it form? It form a double bond here. Okay, this bond here will no longer be here. So we can say this bond is out. What would be for if you form a double bond here? So it means that at the end of the day, what you are going to form is there's no linkage between this and this again, because this one is not forming its own double bond, while this one is not forming its own double bond, right? But that is just an illustration. Let me put it back. And then the product of the reaction would be final product. We said when this one comes up, it forms PH3. Are you getting it? Then P, then double bond word oxygen. Then this other one, when it comes here, what will it form? It forms arrow. Then you have C, double bond C, arrow, with what? Arrow and arrow. Now this is an alkene. I can decide to write it in the way it ought to be written, which is arrow and then C, double bond C, arrow, arrow, arrow. Now this product here is called an alkene. This product here is called an alkene. And this is called a triphenyl phosphine. Okay, triphenyl phosphine. So this is the product of the mechanism for the Wittig reaction. So if they say write the mechanism for the Wittig reaction, this is what you follow. Okay, now let's practice some question. Let's see if we'll be able to use this one to actually get follow the same procedure and see if we'll get the answer. Now say give the product of the following reaction, also stated the mechanism. Now this is an alkyl. This is what? An aldehyde, right? This is an aldehyde. Now this is a carbonyl compound, aldehyde. And then what do we have here? We have this phosphorus yield, but this is the what is it called? The other form of it, which is the other resonance form of it. So we must make it in the form that has that positive charge and negative. Now how do we achieve that? It's very easy. We take this one to this side. Now when we take this one to this side, what will happen? Here becomes positively charged and here becomes what? Negatively charged. So if I want to rewrite this again, I can decide to rewrite this. Then we have something like this. We have C, double bond O. Okay, let me put the double bond O upward. So we have C, double bond O, and what? Hydrogen, right? Then we have this phosphine group here. Okay, phosphine group is something like this. You have the phosphorus, we have the carbon, which is CH2. So I can decide to write this CH2. Then this CH2 is negatively charged, okay? And then we have the phosphorus group, which is positively charged, right? And then we have the PH3. This is still the same thing what we have here, because I told you that when this one packs up here, what we are going to form is something like this: PH3, right? P, positive charge, then CH2, negative charge. Okay, so that will be the product of the reaction. So when this negative charge now comes to this point, what will happen? This one here will pack up to form a negative charge. So the product, according to what we have been doing, so the product will be equals to, sorry about this, you are not supposed to use this pen to indicate. So this one comes here, we say this one will do what? Comes up here to form a negative charge. So the product of the reaction now will be equals to this. You form something like this, right? Something like this. Here becomes O minus. Okay, no, first you have C, There you have O negative. There you have hydrogen, okay? And then you have CH2 here, right? And then you have P positive with PH3. Now, this is the betaine that is formed, right? According to what we know before now. This is the betaine that is formed, which is... Now, what did we say? That there will be ring closure here, right? There is ring closure. This one closes with this. Are you getting it? Then that product will be equal to, when that one closes, it's going to form something like this. You are going to form carbon. Let me erase this. Oxygen, phosphorus, CH2, this PH3, and then this is what? Hydrogen, right? Now, at this point in time, what do? We say the ring will collapse. So when the ring collapse, what do you think is going to happen? This one will pack up here to form a double bond, while this one will pack in here. So the product of this reaction will become something like this. You form an alkene, which is something like this. Double bond. You form C, right? Now this C is having a double bond with CH2, so we can decide to put it double bond CH2. Are you getting it? Plus this phosphine is double bond O, then oxygen, then P, which is trifinite phosphine. So this will be the two products. Now, if you want to write it according to what is in the material, you see something like this. Now, don't fidget on what you actually saw on that material. You can decide to write it like this. Now, what is this one telling us? Oh, sorry about that. Let me say plus here. Then if you want to write it according to how it is written on the material, it's like this. Now, what is this one telling us? This carbon here is this carbon, right? Then double bond, CH2 supposed to be here, but you can't indicate that when you are writing line structures. Now, in the textbook or in the material, you saw something like this. I believe, if I'm not mistaken, saw something like this. Now, they are the same thing. Are you getting it? They are the same thing, just different orientation. Are you getting what I'm saying? Yeah, the same thing. So that is the product of this reaction using the Wittig method. So if you understand the mechanism before, everything becomes very easy for you to understand. And one thing with organic chemistry is it deals with practice. The more you practice, the more you see that everything is the same. Just maybe a slight change in one or two of the parameters. Okay. So now, having learned this, we can now use a very short method to actually propose mechanisms of reaction. Using a very short method, I'm going to teach you that short method to propose the mechanism of the reaction. Now look at this. You have give the product of the following reaction. Now the reaction given to you is this, then plus this. Now whenever you are given anything like this, the first thing you do is write out the reactant, the carbonyl reactant, which is this, right? I'm going to do this in just a single step. Now you are going to see it, maybe single step or two steps. Now you have the double bond oxygen, then you have these two bonds here. Now what you have here is the phosphine, right? Now I can decide to make this thing a little bit. Let me erase this from here first. We are going to put it back, but the reason why I erased it from here is so that we can have, or let me just put it small here. The reason why I decided to do it like this, so that we can have space to write this our group here, the phenine group. So when you react this with this, now this is how to do this particular one. What you do is write this phenine group on top here. Of course, everyone knows what will happen here when you are giving something like this. This one will pack up here. Here will become positive charge, here will become negative charge. So this product becomes PH cos 3 P, then positive charge, and then CH and CH3 with here negative charge. Okay, so what you are going to do is to write that positive charge. Okay, then you write pH3, right? And then you write the CH negative and then what? CH3. Now everything, we are going to do everything in just one single step, right? Now what I'm going to do now is cyclo addition reaction, 2 by 2 cyclo addition reaction, such a way that this one will attack here. If this double minus is attacking here, what will happen? This one will come up, right? If this one is coming up, what will it form here? To form a double bond, I mean a negative charge here. So if I will erase this according to what we have now, what we are going to have, there will be no bond here, and then you have a negative here, and then there will be a bond between this carbon and this place here. True or false? True. Now the next step is this will form a closure, right? So the closure will come here. Now if it forms a closure, what will happen? There will be a bond or a linkage between oxygen and phosphorus, and then this bond will no longer be here. So the final step is the closure of this bond, okay, or the collapse of the ring. So how do the ring usually collapse? This one will come up here, and then this one will what? Will come here. Are you getting it now? And then finally, the product of this reaction, you see that I did everything in one single step. Product of this reaction will become something like this. To become something like this, okay? So we have these C bonded to what? CH2. There will be a double bond here, right? So I can decide to put this double bond here, C. Are you getting that? H, then CH3. It's still the same thing. C double bond, right? Then CH, C double bond, CH, then CH3. Can decide to orient it like this so that we can have space to put these our two bonds here. And then finally, we can write this. If you are writing only the line structure, it means we don't need to actually show the carbons there. So we'll have something like this at the end of the day. And that's what you have in the material, which you have this, and then you are going to have this coming here, and then the double bond here. So this is the product of this reaction. Now in the same vein, you can also practice for this one. So let me erase this. I write the product here quickly so that we can practice for the next one. So the product of this first reaction is something like this. This, and then you have this, you have this, then you have this, and this, and this. So this will be the product of this reaction. Now let's try for this other one. According to what I gave to you, what do? Everything can be done in just one single step, right? First of all, we'll bring this one up here. When this one comes up here, what will it become? Negative. Here becomes positive, right? So write out our carbonyl compounds out. Carbonyl compound we have is something like this. Sorry about that. You have double bond oxygen. Now this phenyl group you have here, I told you that when you are writing it, you first of all put the phenyl group here. Then what is attached to the phenyl is pH3. Okay, then you now have, you know, when this reaction occurs, this whole stuff become pH3 P, then here is become positive, here becomes what? Negative, right? And then here become C2H5. Okay, same thing is what I'm trying to explain here. Okay, all right. So is this correct? This double bond, no, this is not correct. This is supposed to be CH, then CH, COO, like that. Now when this react with this, here become negative, right? Which is this, then we'll have CH, then we'll have COO, C2H5. Now the reason why I'm doing it like this is so that we can have the species that are reacting with this out. Are you getting? You can bring them out. So at the end of the day, what do you think we are going to have? This negative charge here attacks this. If it attacks this one comes up. Abi, that is the step. So when this negative charge attacks this, what are we going to form? We are going to form a linkage between here and here. Then when this one pass up, you are going to form a negative charge here, right? Now we say the next step is the negative charge will form intramolecular closure to form a ring. So when that intramolecular closure occur, what will happen? We'll form a linkage between this and this. So we erase this, form a linkage between this and this, right? Now the last step is the ring collapse. So when the ring collapse, this one comes up and this one comes down. So you see how easy it is, right? When this one comes down, what do you think we are going to form? We are now going to form, let me write it here. There's no space for that. Let me look for somewhere and write it so that at the end of the day we can transfer it here. Okay, let me write it here. We have something like this at the end of the day. This will now give us the double bond will be formed between this and this, right? So I can decide to write it. If the double bond is here, I can decide to write it upward like this. Abina, any position, because this down is because of the way the reaction reacted. I can decide to write it up. So we have C double bond. Then what do we have here? CH. Abi. Then what do we have? We have CO and then C2H5. Okay, plus the phosphine, which is double bond O, trifinite phosphine, which is like the byproduct of the reaction. Okay, so that will become the product of this reaction. So the product will be finally this double bond CH CO C2 H5 plus then we have O, which is trifinite phosphine PH3. This is the trifinite phosphine, which is the byproduct of all Wittig reaction. So you see how we can actually solve Wittig, any problem on Wittig reaction. Now we have a question here. It's sort of fortunate that I didn't give space to actually to work on this particular question. Now the B part of this question, everybody can do it. This is the self rule, elimination reaction. Now it's a Rayfit pharmaceutical company synthesized methylene cyclohexane ring using the outline below. Suggest an alternative route to improve the yield of the minor product to 85% yield, illustrating the reaction mechanism, reagents to achieve the desired product, and then state why B is the major product using the self rule. So let's go straight into this. Now the initial reactant that was given was this, right? Now the question says that we should suggest an alternative route to improve the yield of the minor product to 85% yield, illustrating the reaction mechanism, the reagents to achieve the desired product. Then the B part of the question says, state why B is the major product using the ZSF principle. Now, when I started explaining the Wittig reaction, I stated that the Wittig reaction is a reaction that is used most times for synthesizing alkene that may come out as minor products in other reactions like the ZSF reaction. You know, there are different reactions for actually synthesizing alkene, and this Wittig reaction is just one of them. So some of the compounds or some of the methods that may actually yield some compound as minor products may yield this compound as major product when it comes to the Wittig reaction. So what we have to do is, how do we actually synthesize this minor product as a major product? And the only method we can actually apply to do that is the Wittig reaction. So let's suggest it. The reaction, we are just asked to write the reactions and the reaction mechanism. So what we are going to do is to write the reaction first. The reaction first will be, I think we've done this before. The something given to us was this, right? And then you have OH, right? Now, I think this is the cyclohexanone. Okay, name of this product reactant is cyclohexanol. Now, first of all, cyclohexanol is an alcohol. But what we actually need for this reaction is a ketone or an aldehyde. That is a carbonyl compound. So the first thing is to oxidize this. Now when you oxidize it, it gives you potassium. You use sodium dichromate or sodium heptazodichromate and H2SO4. Now when you react these two together, react it with cyclohexanol, it's going to give you cyclohexanone. Okay? So this is going to give us cyclohexanone. Now, this is double bond oxygen, which is called cyclohexanone. Okay? So this is called cyclohexanone. Now, when this cyclohexanone undergoes the Wittig reaction, what do you think is going to form? It's going to form the product that we are looking for. So which of the reactants or which of the ylides are we going to use? So we are going to react this with CH2, which is the ylide, because we need to know the choice of ylide that will give us that product, and the only one is the simplest ylide, which is the one with CH2. So this gives us PH3, right? P positive with CH2 negative. So when we react this with this, what we are expecting to get is that product that we'll have. Now, according to what I taught you or what I've said before, what I'm going to do now is to write this, orient this in such a way that it can easily react with this. Okay, so what we have here is something like this. You have double bond. Let me make it longer. Right, double bond oxygen. Then we have P positive, and then you have this P positive has PH3, and then you have CH2 negative. Now at the end of the day, what did you say we are going to do? This one will pack in here, right? And then this one will pack up here. So if we have that, the product will be equal to, you have something like this. Here becomes negative, right? Then there will be a linkage here. Here becomes CH2, and here becomes P positive PH3. And we said the name of this product is betaine or betaine. Now the next thing is this one comes to this phosphorus negative, comes to this phosphorus, and then there is a closure here to form a ring. So that will give us sorry about that, that will give us something like this, which we are going to have O P PH3, and then we have CH2. Right? Now at this point in time, what do you say is the next step? The ring will rupture. Now if the ring ruptures, you have this one comes here, this one comes here. So the product of the reaction would be equal to this, gives us P. Okay, this will no longer be here again. There will be now recall that as this one is coming here, double bond will be formed here, so we can write it on top here as what? CH2. True or false? Is true, because this one now will now form a double bond here, and instead of writing double bond, now what I'm trying to avoid is writing a double bond that will be going this way, CH2. It doesn't make so much sense, so you have to put it on top. Orientation does not really matter here unless you are talking about stereochemistry. Are you getting it now? Plus, what are we going to form here? Of course, you know a double bond will be formed here, which is the trifinite phosphine oxide. So this will be P, or I can decide to write it as PH3 P double bond O. So this is the major product. 85% of this will be formed. So you now see that we can actually use the Wittig reaction to actually get this product to 85%. Are you getting it? Instead of using this synthetic route. This route is the one that uses Grignard reagent, whatsoever, alkyl lithium. To it adds the alkyl lithium here and then continues like that. But we are not going to use that method here. Now, the next one says state why B is the major product using ZSF rule. State why B is the major product using ZSF rule. So which of them is the B? Now the next one says states why B is the major product using ZSF rule. The first thing you need to know is what is ZSF rule. Now ZSF rule is a rule that is used for eliminating water from alcohol to form alkenes. Are we getting it? When water is eliminated from alcohol to form alkene, it either follows the ZSF rule or the Hofmann's rule. Now, the products, we are going to look at the equation and see where we can actually pick up the ZSF rule. Are we getting it? We are going to look at the product and see where we can actually pick up ZSF rule. Now, we can pick up ZSF rule from here, right? Because this is where the alcohol is. Are you getting it? Don't start from here. Is that understood? Don't start from here. Let's pick up this product here. And then from here to here, let's see the one that will give us the ZSF rule. Now, what we are going to do is... so that's what I've written here. Now, what is the principle behind the ZSF rule? It says that whenever the elimination reaction occurs, because you are eliminating water, that the more substituted alkene is formed as the major product. The more substituted alkene is formed as the major product. Now, in other words, it means that you should actually remove the or let's say in that case we have more than one beta carbon, right? We have more than one beta carbon. Now, in this case, what is the beta carbon? Now, this first carbon here is called the alpha carbon, right? Now, this first carbon here, where each of these things are attached, are called the alpha carbon. Now, this is a beta carbon. Are you getting it? This is a beta carbon. And then this is a beta carbon. Now, what does that suggest? It means we can either eliminate from here or eliminate from here. Okay? But in this question, they didn't actually point the one that is... no one was pointed as B here. Okay, why the one that is a major product is a major product? Because no one was pointed as B here. Are you getting it? So what we are going to do is we take this one. This is a major product. So this becomes B and this becomes what? A. Are you getting it? We want to show why, according to this one is a major product. Okay. So what we are going to do is come here. Now, according to this same way you are eliminating, recall that we want to remove water, which is OH, H2O from here. Now, according to this say when you are eliminating, you remove OH and then one hydrogen from any of the beta carbon to form a double bond. Now, the question is, which of the beta carbon are you going to remove from? Are you going to remove from this one or this? Recall that these two are the same because they are the same side of the circle, right, of the cyclic structure. These two are the same. So you can either remove from here, here, or here and here. So which of them do you think is having the lesser number of hydrogen? Or let me tell you, when you are eliminating according to the ZSF, you pick two beta carbons. The one that have lesser hydrogen is the one you should eliminate from. That one will give you the major product. So which of them do you think is having the lesser hydrogen? Is it this? Recall that this is a beta carbon or this. Now, we can decide to put C here. Now, if you put C here, these are already two bonds. It means there are how many hydrogens here? There are two hydrogens here, right? To make the valence to be 4, because this is 1, 2, then 2 hydrogen, making it to be what? 4. So this one is having CH2, when this one is having CH3. So which of them have a higher number of hydrogen? Now, you agree with me that this is having a higher number of hydrogen, while this one is having a fewer number of hydrogen. And according to the ZSF rule, eliminate from the one that has a fewer number of hydrogen, right? So if we eliminate from here, it means we remove the OH from here, which is this one, and then remove hydrogen from here. So I can decide to bring out the hydrogens like this. Let me make it a little bit easier. by saying this is hydrogen, this is hydrogen. Normally this is a beta carbon. So if I remove hydrogen, one hydrogen from here, right, and I remove one hydrogen from here, right, I remove OH from here, it means that a bond will be formed between here and here, right? So the bond will be something like this, and here will be a double bond, right? Then you have one hydrogen here. But when you are writing line structure, you may not really need to show this hydrogen again. There you have, there's no OH here again because you remove this OH, elimination reaction. Then in this case you have CH3. So this is the reason why this is the major product according to Zesef rule. So this is the major product according to Zesef rule, and you know why now. I've explained the reason why. Because Zesef rule states that the more substituted alkene is usually the one with the major product, in such a way that when you are eliminating between the two beta carbon, eliminate from the one that have the fewest number of beta hydrogens. Are you getting it? Eliminate from the one that has the fewer number of beta hydrogen. So at this point in time, I think we've been able to do justice to the Wittig reaction. Now, what is the usefulness of the Wittig reaction? Now, the Wittig reaction is used to synthesize naturally occurring B-carotene that is found in fruit like apricots, carrots, etc. Are we getting it? It's used for synthesis of B-carotene, naturally occurring B-carotene in apricots, carrots, and some other things. Are we getting it now? B-carotene is pro-vitamin A. That means before vitamin A, what you have is B-carotene. Then the preparation of alpha-beta unsaturated esters, it's used for the synthesis of alpha-beta unsaturated esters. I'm going through the material to see if there is any place here that I've not actually touched in this reaction. Alpha-beta unsaturated ester. You can also use that method to synthesize them. How do we do that? It's still the same thing, the same approach. Okay, the same approach like the one that we have here. We have a reaction here like that. We use it to synthesize alpha beta unsaturated ester. It's very easy. Now this is phosphine, right? pH3, or let's say this trifinite phosphine. We say this one has a lone pair of electrons, right? It has lone pairs of electrons. Now when this reacts with this Cl, CH2, COOET, now what do you say happens in this situation? As this one is coming in to meet this, what will happen? This one, or let me write it in the way that it will be very easier to disseminate or to understand. This same structure here, let me write it down. The structure is Cl, CH2, COOET. Now I can decide to write it as carbon, right? Now I can decide to write this one as what? Cl. Then up here I write COOET, right? And then here I write hydrogen here, and then finally hydrogen here. Okay, now according to the principle I told you, that when you are making your halide, your phosphorus halide, what happened? This one here will attack this bond. Can you still remember when we are preparing phosphorus halide? Go and look at the method. Then this one we get out. Are you getting it? As it's getting out, what will happen here? There will be a linkage between this. So this product will be equal to something like this. You form pH3, then P, then you form C. Now this will be COOET, and then here will be what? Hydrogen, and here will be what? Hydrogen. Now if you react it with the product that you have here, you have this same thing is what you have here as pH3. If you look at your material, you see something like this: PCH2 and then COOET. Look at it: pH3, P, then CH2, CH2, then COOET. Still the same thing. Are you getting it now? Now if you react this with sodium ethoxide, now what did I say? Sodium ethoxide. Sodium ethoxide is a base. Are you getting it now? Sodium ethoxide is a base. Are you getting it now? So the sodium ethoxide will form negative here. Now that negative can easily come and abstract a proton from here. Now, if that negative abstracts a proton from here, it means that this one will kick in here to form a negative charge. Now, we said that whenever this one is coming here, it has given up some electron to this, so here will become positively charged. So this one comes here to become what? A negative charge. So the product of this reaction will be something like this. PH3, P positive, and then you have C. Here becomes COO ET, and here becomes H. Here is what? Negative. So we said this is our halide. This is our phosphorus halide. Now, if the phosphorus halide now react with phenine, benzaldehyde is something like this. That structure you see there is something like this. Benzaldehyde. Okay, let me put it up here. Right? This is structure of benzaldehyde. Are you getting it now? So, if this reacts with benzaldehyde, this is the phenine, this is the phosphorus halide. Okay? Let me use a red pen. Now, when this phosphorus halide reacts with benzaldehyde, structure of benzaldehyde, what is it going to form? Now, I told you the way this whole thing reacts. Let this phenine group come up and this one comes down so that it will have space to react. So what are we going to form here? Of course, you know this is C negative. Here will be C negative, right? Here will be C negative. And then what are we going to have up here is the phenine ring. Phosphorus, triphenyl phosphorus rather. And then we have, let's say this under here is hydrogen, and then you have COO ET. Now, what did I say is going to happen here? Shortcut, quick way. We say this all will come here, and then this all will what? Go up. And then if that happens, what do you think is going to happen? It's going to form a bond here, a linkage. So when this one forms a linkage here, means this negative is no longer there. This one is here. The double bond is no longer here. And then you have negative here. Now, quickly again, what will happen? This one will form a ring that will close this up, right? According to what we said, this positively charged. So when it forms a ring, this positive charge will no longer be here, and there will be a closure here. You see the same method that we did for the other one. Now, finally, the final step is when this one now we form, the ring will rupture up, and then you form the final product. Final product for this reaction will become this phenine ring, right? Then you have C, right? Now this hydrogen, Abi, this double bond here, there will be a double bond here because as this one is coming here to form a double bond, so I can decide to put the double bond here, C, and then we have our COO ET, and then what? Hydrogen. Now, if I want to write this in the manner at which it was written in the material, we'll be having something like this. Recall that this is a phenine ring, right? I can decide to bring it out and say this phenine ring, let it be pH. So I have this carbon here in the center. Phenine ring is what? pH. I use pH to indicate it. Then we have what? Hydrogen. Then double bond, right? Then carbon. Then we have hydrogen, and then COOET. So you see that the method, the something is, if you understand one of the method, then every other one becomes very easy for you. So this is what we call alpha beta unsaturated ester. Alpha beta unsaturated ester. Now, why do we call it alpha beta unsaturated ester? It's pretty easy. Alpha beta unsaturated ester. Now, I was asking, why do we call it alpha beta unsaturated ester? It's pretty easy, right? Is because the phenine ring here, the ester group is what you have here. Now, the ring after the carbon after the ester functional group become the alpha. Why the one close to it becomes the what? Beta. So you see that between alpha and beta there is what? A double bond. So we call it alpha beta unsaturated ester. Between the alpha and the beta carbon there is a double bond. Are you getting it now? So the Wittig method can also be used in preparation of alpha beta unsaturated ester. So our next class will be on organometallic compounds. organometallic compounds like Grignard reagent that were synthesized by Vito Grignard, etc. So we've done an exhaustive study of the Wittig reaction, and in every application of it, we said it is used for the synthesis of what? Of provitamin A, which is beta carotene, that is seen in apricot and other these things. Thank you very much for your time.